Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. And in this video, we will continue our discussion of finite Fourier analysis. Let me remind you from the previous video that we discussed the inner product of two periodic functions. We will always fix a period B. And whenever I write Xi, I mean this sort of first bth root of unity, e to the 2 pi I over b. And let me also remind you that everything boiled down to this sort of orthogonality relation between roots of unity. We will see this again today. In this business, we often have sums like this one over roots of unity, and the sum collapses and acts like a sieve. The first thing I'd like to discuss now concerns the inner product that we also defined in the last video. It turns out this inner product remains essentially invariant if we move from two functions, like here f and g, to the inner product of their Fourier transforms, and this is called the Parseval identity. Yeah, so this is theorem 7.8 in a book. It says the inner product of f and g is up to a factor of b equal to the inner product of f hat and g hat, the Fourier transforms. And if you think of inner product as philosophically measuring a distance, then what we're saying here is that the distance of the original functions equals the distance of the Fourier transforms, again up to a factor of b. Okay, let's prove this, and again, just like in the last video, I will prove things from scratch, but I want you to notice that we have sort of this orthogonality relation showing up naturally, and it will play the same role as in the previous video. So let's compute the inner product of f and g. So by definition, I pasted it on the right, just so you can recall everything that we've defined so far. This is a sum over k, and we're summing fk times the conjugate of gk. And my sums today will always be from 0 to b minus 1. We'll have lots of double and triple sums. So let me just abbreviate this and write a little k under the summation parameter. Yeah, so here already comes a triple sum, so I will now replace f by its Fourier series. So my outside sum is over k, and then let's say my Fourier series is over m. So I have my Fourier coefficients and then my exponential. So this will be xc to the k times m. And then I have a similar sum, let's say, over n for g. And we mustn't forget that we are taking the conjugate of g. So that means we need to conjugate everything in this sum. So the coefficients just get conjugated, and then my exponential conjugation means introducing a minus sign. Yeah, so if you remember, xc is this root of unity, and that means that xc conjugate will be e to the negative pi I over b. Okay, so now we reshuffle our sum. So my outside sum will be on m and n, which means I can write now the Fourier coefficients. And then my inner sum will be over k. And so now you can see what happens. Here come the orthogonality relations. Yeah, so this inner sum over here is 0. unless m is equal to n. As always, you really have to say m is congruent to n mod b, but because my sums over m and n are all from 0 to b minus 1, what I get here is equality between m and n. This orthogonality has the same effect as previously. Yeah, so let me remind you of what happened when we computed Fourier transforms. You had an inner sum that sort of sieves out one coefficient. And so now in our situation is we have an inner sum that sieves out one coefficient, let's say on the sum over n. And so for the sum over n, the one coefficient that remains is n equals m, and then I have my outside sum over m still. But the inner sum now disappears, and we're replacing n by m. And now let's be a little careful. So if m is equal to n, the sum over the roots of unity was a b, so we'll have a factor of b here. And this is precisely the statement of theorem 7.8. So by definition, what we have here is the inner product of the Fourier transforms of f and g. Let me give you an application of this theorem and introduce the main character of the next chapter. This finite arithmetic sum that you see here on the top left is called a Dedekind sum. And we will see in chapter 8 that this is an important ingredient in Erhard polynomials and Erhard quasi-polynomials. Anyway, let's just take this at face value. If I think of this as an inner product, then I see two functions over here. So maybe let me call this f and g like before. So one of my function is a sawtooth function, and the other one is the sawtooth function sort of perturbed by this multiple a. A here is just another integer, and you should think of this Dedekind sum as a function of two parameters. Okay, so our theorem from the previous slide says we need to compute Fourier transforms. So for f, we've done this. So let me remind you, this was our example from the previous video. So the Fourier transform is essentially a cotangent function. I over 2b times the cotangent. And so I don't want to repeat this calculation for g, but we will use this Fourier transform for f already. So let me show you a trick. So my Fourier transform for g, by definition, is sum over k of my function g against an exponential. And so just once I will write that my sum goes from 0 to b minus 1, because what I'll do now is a change of variables. I will replace k by k times a inverse. And by a inverse, I mean the inverse of a modulo b. So I need a condition over here that I can compute this inverse. So here we need to assume that the GCD of A and B is 1. Otherwise, A inverse does not exist. But I hope you can see why I'm making this change of variables, because if I now plug in K times A inverse instead of A, my sawtooth function over here sees an A inverse times A, and because the sawtooth function is periodic modulo b, I can replace this A inverse A by a 1, and that means I just see a k over b. Let's do this change of variables. Multiplying k by a number that's relatively prime to b, A inverse is still relatively prime to b, permutes the index set that I'm summing over. So this sum now gets shuffled around, but I'm still summing from 0 to b minus 1. And so now multiplying through by A inverse, as we just saw, has the effect that here I see just a sawtooth function of k over b, and then I am seeing the A inverse over here because I used to just have a k here. So now I can think of the function above. I can think of this variable as replaced by A inverse n, and then you can see the Fourier transform of the sawtooth function as above. So that means this Fourier transform is the cotangent again, but my variable is not an n, it's an A inverse n. Okay, after all this prep work, let's use theorem 7.8. The way I'm setting things up is that my Dedekind sum is the inner product of f and g. And so, by what we proved on the previous slide, we can write the Dedekind sum also as b times the inner product of the Fourier transforms. And so that means I can write the Dedekind sum as a product of cotangents. Let's be a little careful. So I have for the first Fourier transform, I have an I over 2b cotangent pi n over b. For the second one, I have an I over 2b times the cotangent of pi A inverse k over b. But I need to conjugate this. Well, the cotangent is a real number, no problem. So this I over here becomes a negative I. So now I will do a similar change of variables as we did when computing g hat, except that now I will change k into A times k. So this has the effect that, again, we're just permuting the summation index. So again, we're running through all k modulo b. I should figure out the constant up front. So I have a minus I squared and a b over 4b squared. So that's a 1 over 4b squared. And now I'm using the fact that cotangent is a periodic function. So my change of variables now says that I have a Ka in my first cotangent. And very similar to what we did before, if I now see a cotangent pi A inverse times A times K, because cotangent of pi x is a periodic function, I can replace A times A inverse by 1, and I have this cotangent representation of the Dedekind sum. We finish with one more appearance of the orthogonality relation. So this is the convolution theorem now. The convolution of two periodic function, we used the symbol star for that, f star g, is given by this definition up here. If you've taken a course in Fourier analysis, you've seen something very, very similar like this, except here we have discrete objects, and so our convolution is defined by a sum. As always, I assume that f and g are periodic functions with period b. And the point of this definition is really to make theorem 7.10 here work, and that is the convolution f star g is precisely the function that has the product of the Fourier transforms as the new Fourier transform. Yeah, so we assume that f has some Fourier coefficients ak, and g has some Fourier coefficients ck. And to make this all look nice, I have a factor of 1 over b in front of my sums. Then with the same factor, the convolution f star g has Fourier coefficients ak times ck. And so, to see the orthogonality relation at work one more time, we'll go through this now. And again, I'm going to write just a summation index because all of my sums are again from 0 to b minus 1. And we will see triple sums in a moment. Because of course we're going to replace f by its Fourier series. And let's be a little careful, as a 1 over b outside. So let's say I'm using index k for f, so my coefficients are ak, and then I have the exponential here, k times t minus m, which is my variable over here. And then I have another Fourier series, another 1 over b for g. So let's use index j over here. G, I have a coefficient z, j, and then my exponential goes with j and times m. Okay, and so now you should expect what happens. I'll make my outside sum over k and j. And so it's really a parallel computation as what we did 2 pages ago. I have an ak, cj, and I can actually take a xc to the, I guess, kt out of my inner sum, which will be now over m. And so what's left is a xc to the m. We'll have a j and a minus k. Okay, and so here it is. Here are the orthogonal relations. This will be 0 unless j is equal to k, and exactly the same sieving now happens as we had for the Parseval identity. So we're left with, if the outside sum, let's say, is over k, then my sum over j disappears. I only get the term when j is equal to k. So I get an ak, ck, and then my exponential. And so when j is equal to k, my inner sum is b, so what's left is a 1 over b here.